Okay, I have started the recording. Let's begin with a few announcements here. Office hours. Okay. So here's the situation with office hours this week. As you know, we got the final, right? Final exam on Thursday. Okay, so because we have the final exam on Thursday, I'm going to be having office hours with an extra office hour on Wednesday. So here's what we're going to do. Okay, so that's a nice quick summary. It's understood each one of these is a 1 hour installment. So tonight we got office hours at 8 o'clock, 8 p.m. Ditto for Tuesday tomorrow. And the same is true Wednesday, but furthermore, Wednesday we've got the morning session as well as the evening, like so. Okay, of course, the big announcement here is course evaluations. I'm kidding. The other big announcement is the final exam. But I do want to take the opportunity here to remind you about the course evaluations. Okay, so please take the time to do the course evaluations because your feedback is important. Okay, and again, yeah, the big ticket item, of course, is the final exam. On Thursday, there's going to be a morning session and an evening session. It'll be a 3-hour exam. That's the guidelines we have from the administration. Then you get 15 minutes to prepare your PDF file and upload it. So I will provide some more details. More details on the final exam will be posted later today, as well as a sample exam. Okay. So that's kind of the situation here with the final exam approaching very quickly. What we're going to do now is we have a few topics in chapter 13. We'd like to make some closing remarks on the wonderful world of the Hamiltonian formulation of classical mechanics. Then we proceed into chapter 12. And again, that's not a contradiction in the sense that after you finish chapter 11, you can do the remaining chapters in whatever order you like. That's what Taylor says. Okay, so everything's cool here with chapter 13 coming before chapter 12 in our course, enabling us to put chapter 13 on the final exam. Chapter 12 will not be on the final exam. So if you look at what we're doing this week, we have 3 lectures remaining, right? Monday, Tuesday, Wednesday. Because the final exam is on Thursday, there's no lecture on Thursday. Perhaps I should emphasize that here. We do have a natural progression here Monday, Tuesday, Wednesday. Thursday, so this fits together very nicely. And furthermore, we can make some remarks on chapter 12, where we introduce the notion of discrete time, right? Especially important for your homework. But let's just quickly remark Thursday, final exam. No lecture. Okay, so the remark that I just made there about the discrete nature of time for the homework assignment, let's take a second to talk about that. In chapter 12, we will study some fascinating dynamical systems. All right, most notably the damped-driven pendulum. This is a chaotic system with 1 degree of freedom. And when we study the system, we should begin by observing that it's the usual mechanical system in the sense that we'll solve for the position, this notion of the position of the pendulum as a function of the usual time which we have a continuous t-axis. The time axis should be thought of as kind of like a real number, a real axis. We have a continuum. For the homework assignment, you're doing something different. You have a discrete notion of time, so time becomes an integer. We still do talk about a lowercase t, but it's understood as you go through section 12.9, which is what is needed for the current homework assignment. It's understood that you have an integer. Time has become an integer. The reason we do that is it's much easier to work on a computer with something like the logistic map, okay? And I kind of mentioned you have that structure here, Monday, Tuesday, Wednesday, Thursday. You see how we're stepping through this list, okay? So there's that notion of step, step, step. That's what we're doing in section 12.9. So we'll make a quick remark here. Section okay. So time becomes an integer. Fascinating concept. Oops. Can I fix it? Yes, I can. Okay. So the time axis is an integer. And you can see this in the plots, et cetera, and so forth. Let's take a moment to talk about the most fundamental relationships here. As you know, we have page 502. So the central premise here is that you have an iteration. This t is an integer. Let's use a different color here. And so it's meaningful. You can see from this formula here, we have a t plus 1. That's not t plus 1 second, it's just t plus 1. Therefore, it must be true that t is dimensionless. Anytime you add two things, they have to have the same dimensions. So we're adding a pure number. This plus 1, that's a pure number, it's an integer. So you can see right there, the time is an integer. And here, okay. So this kind of mapping, as you know, is called an iteration. The explicit formula now for the logistic map and it's a nice opportunity to remind ourselves of something we've seen throughout the course. Okay, we must be very fluent with the notion of an abstract function. So here we have a function of a single variable. Our friends in the math department would write it like this. Okay, and so notice this is the arrow without any sort of feature at the left end. Okay, that means this particular statement here is the following statement. We have a function f, it's a mapping from the set of real numbers to the set of real numbers. That's this first statement. The next statement we'll make is how a typical element gets mapped. And here a different style arrow is used because this is a different statement. We're saying a real number t gets mapped to f of t. All right. So this function has a well-defined existence, logically distinct, right? The existence of this function f is logically distinct from this mapping here. Here we have a mapping. You have some value x sub t. This formula produces the next value, x sub t plus 1. That's the next value in an infinite sequence of x values. So here we define a sequence using the function. Okay, but let's appreciate the function has an existence unto itself. Okay, and what is that existence? I'll use the notation in the text. Well, actually, you know what? I'm not real happy with my choice of t here. You know, we're going to need to fix this. We're going to need to fix, okay? And somebody walked off with my correction tape. Yeah, I'm going to have to do a pretty extreme write-over. Okay, sorry about that. Yeah, I like this better because I was just emphasizing t as an integer. Let's continue to use that notation for this discussion. Okay, and the particular formula now for the logistic map. Okay, so here you have the logistic map, and notice the remarks we made a moment ago. This x is a pure number, and the reason you have one is you have 1 minus x. This is not 1 meter minus x. This is just 1 minus x, okay? So for this analysis, we're working with a pure number x. It is a real number. That's why I wanted to kind of switch notation here. X is an element of the real numbers. The mapping, again, produces an element of the real numbers. So once again, this r is a pure number. And typically we call it the growth parameter. The reason it's called the growth parameter is if you think of, for example, small positive values of x. Suppose x is a very small positive number, such as 10 to the minus 10. Okay, very small. Then over here we have the 1 minus that very small number. This second factor, which is in parentheses, is very close to simply being unity, 1.0, very close. And so you see when x is small, we just have r times x. All right, so let's record that observation here. If x is small, so we'll say if the magnitude of x is small, well, let's be rigorous here. Anytime you say small, you must say small compared to what? You can't just say small. So we'll say if it's much less than 1, then we have a simplified story. This f of x is approximately okay. So you see what's happening here. We have this portion of the picture. Let's be very clear. This portion of the discussion, and I've put a box there, and we have a big box. This portion is devoted to the function f. The function f has a well-defined existence. All right. Notice we've been speaking of f of x, right? That's because the function f is a function that takes a single variable as an input, and it returns a single number as an output. The decision to use the function here for an iteration is completely distinct, okay? Both of these are perfectly logically sound, but here, in this equation, which also occurs on 502, I've just rewritten it slightly, we've defined an infinite sequence. So here, the function f is used to define an infinite sequence. And this word sequence is a very good choice. It really captures the essence of what's going on. Think of just a sequence of numbers that goes on. You can step along this sequence and look at the numbers. How would we describe this a little bit more accurately? Well, if you have this kind of a sequence, then this again is a mapping. It's a mapping from the integers. Okay, there's the integers to the real numbers. Okay, and if you like, you could say the integer is greater than or equal to 0. You can attach that here as a little subscript. So this little subscript says greater than or equal to 0. But the crucial thing is the notion of a sequence can be, again, perceived as a mapping. This is different. And now we have the correct usage of the t, right? So an integer t gets mapped to x sub t, right? So it's an opportunity to remind ourselves how the notation works. The idea of having a subscript, you could have written this as x of t, right? Could write, this would be alternative notation. okay? But typically for sequences, we do like to write this as a subscript because we think of that as an index, okay? So let's observe, we have two different structures here. And this is part of a very big message in the course, understanding the functions that are involved. Very often, we deal with functions of multiple variables. Both of these functions here in this picture, we have this box devoted to one function. We have this box devoted to another function. Both of these functions are functions of a single variable. Okay. This one is going from the real numbers to the real numbers. This is the so-called Blackboard bold special font. Okay. And this one's going from the integers, really the non-negative integers, to the real numbers. So these are both very well-defined functions. And it's really an opportunity to talk about the notation. So again, this function f here, we love this, right? We think of this r as a parameter. You could say this is a function of two variables, r and x, right? But very often, as we've seen throughout the course, it's useful to think of some of the parameters as simply being constants. And in that spirit, we think of the r here as simply being constant. So this is a function of one variable. We think of the variable being x and r as some sort of constant, okay? Having said that, we have a very nice mapping here, okay? Once you've defined this, then this equation up here defines a different function, this sequence. There's something that got swept under the rug here. What's the initial value, the so-called x0? Okay, that's, you just choose an initial value. For example, you could choose it to be 1 or some small number. Okay, so we have these two mappings, and then this is really the setting for section 12.9. The reason we're doing this on the homework is it's much easier to deal with these iterations on a computer than to solve differential equations. To solve differential equations such as the damp-driven pendulum, the DDP, we call that the DDP, the damp-driven pendulum. This requires some effort because how do you convince yourself that you have the correct solution gotten via a computer, right? We cannot solve the differential equation using formulas as we have for the simple harmonic oscillator. In chapter 5, we also solved the simple harmonic oscillator with damping and with the driving force. We solved all those problems. But if you have a pendulum rather than a Hooke's law restoring force, then we get a chaotic system and we cannot write down these nice formulas for the solution. We can do it for small oscillations, but the general exact solution, you can't do it. And that's why chapter 12 is such a nice example of using a computer to investigate interesting physics. And that's part of the growing realization that happened over several recent decades that all these hundreds of years of history of classical mechanics, they were in fact kind of obsessed with these problems that you could solve using simple formulas. And we had wonderful solutions like the Kepler orbits, etc. But in fact, most real life problems, you cannot write down a simple formula. And in fact, chaos is ubiquitous. Chaos is all over the place. And there are really powerful theorems such as the KAM theorem, named after three famous mathematicians, I think Kolmogorov, Arnold, and Moser. And if my memory serves me correctly, yeah, the realization that a generic mechanical system has some islands of stability and a sea of chaos. So understanding chaos, really, the advocates would say, is really the correct worldview. It's the most common case for physical systems. Okay, so to do this on a computer, right, you have to use a computer because we cannot write down simple formulas, is one of the messages of chapter 12. And in recent years, the physics department, I mentioned I was part of a committee to work on, introducing programming to a series, I should say a subset of upper division courses. We focused on Physics 105, Physics 112, Physics 130, no, not 137, and particle physics. So that was the emphasis. We're starting to bring in the programming. So that's why this homework number 11 is an important part of the story here. Of course, you do get to drop one of your homework scores. No questions asked. So if you like, you can skip this homework 11. But over the years, sometimes students choose to skip this homework assignment. It's okay if you'd like to do that. But again, the message is it's very useful to get some experience with computers and investigating an interesting problem using a computer. All right, so this is an overview here of what we're doing in chapter 12. Again, section 12.9, which is a must read for this homework, is interesting because we have the time t as an integer, okay, t plus 1. So again, the growth parameter, the reason we call it a growth parameter is if you're in this regime. Notice at the bottom here, I made a remark, if x is small in magnitude. It has a small magnitude, but it's still very important. Let's understand what happens here. This mapping just is a multiplicative factor, right? You just multiply by r. Now, if you repeat the iteration, the next one gets multiplied by r again. So that's r squared times the value we had 2 steps before. So you can see every application of this function is just another multiplication. And you have the usual notion of exponential growth, right? It's exponential growth if r is greater than 1. And it's exponential decay if r is less than 1 in magnitude. If you like, you can put a minus sign there, have it flip back and forth. Okay, so that's the motivation. Why is this called the growth parameter? There's a history to this, and we see the very popular term exponential growth is a special example when x is small, and you'll see this in your experiments. Now, what happens here with this multiplicative factor, we do have another factor here, this multiplicative factor 1 minus x. This serves to put an upper limit on the growth. So you see if this value x increases and suppose it gets to be just a little bit less than 1, suddenly this is a multiplicative factor 1 minus x, which can really knock down the output number and get it smaller. So this serves to modulate, kind of, I should say moderate, the runaway growth, okay? And so this logistic map becomes a very interesting mapping. And we can learn a lot. That's the purpose here on the homework assignment. We learn a lot. There are times, excuse me. As I was saying, yep, there are times we make plots where there's an r-axis. Now, if there's an r-axis, that would appear to contradict what I just said, that we're thinking of this as a function of a single variable. Okay, and that's true. For this discussion, which I put in this box, we think of r as just a fixed parameter, and this function here then is a function of a single variable x. Okay, that's a perfectly valid way to view this equation. But there are other times in section 12.9 where we choose to think about a range of r values. Okay, so there we're thinking of an r-axis, and we can make plots with an r-axis. Okay, so there's kind of a generalization. At times we have different perspectives on the same ultimate mathematics here. So there are times where we very much do think of r as a variable. Okay, so let's go back. We want to finish a few topics in chapter 13. And then we'll investigate the wonderful world of chaos. Now let's look at our situation. This is the last week of the course, right? Here we are, it's Monday. We have office hours tonight, Tuesday, Wednesday, and then the final on Thursday in the lecture. So you see we have these 3 lectures, Monday, Tuesday, Wednesday. Part of what we're going to do, especially on Wednesday, is review for the final exam. Okay, so today we're going to finish up a few topics in chapter 13. We'll start talking about chaos. And then later in the week, we will be doing review sessions here in lecture, reviewing. And one of the best ways to review the material is to make connections between different parts of the course. Okay, so we'll make some interesting connections. For example, we'll bring in chapter 9 and talk about doing physics in a non-inertial frame. Okay, we'll talk about interesting applications. Yeah, I just got in the chat window. Yep, I will be posting a practice final later today. And you'll see on the practice final, some of the problems will be problems from earlier practice exams. That's okay. Remember, the purpose of a practice final is not to present novel material, but to give you a feeling for what the exam will look like. Okay. So now let's talk about Liouville's theorem some more. And you will recall at the end of our last meeting, I was really having a lot of fun talking about what a wonderful theorem this is. And the folks up at Lawrence Berkeley National Laboratory, so relative to the UC Berkeley campus, you go uphill a little bit, just a couple hundred meters, Lawrence Berkeley National Laboratory. And there's a wonderful team of physicists who work on that accelerator. They're constantly striving to improve the machine. And if you attend those meetings, you will hear them talk about Liouville's theorem, right? Phase space density. So this is an example how skills that we learn here in Physics 105 are really important for doing exciting physics, and accelerator physics is very exciting physics, building these amazing machines. So we're going to be talking about the notion of phase space volume. Okay. And if you have a couple billion electrons, another way to say it is, suppose you have about a nanocoulomb of charge in the form of electrons, and you have this amazing machine called the Advanced Light Source. This small group of electrons, they're small because you've gone to great lengths to compress them in phase space. So not only are they close together in physical space, but also their velocity vectors are close together in velocity space. That is to say, if you visualize all these velocity vectors, they're pointing in very similar directions and have very similar magnitudes. If you can do that, the machine produces brighter X-rays, okay? And one speaks of X-ray brightness. Again, this is more than just the intensity. We're talking not only about the intensity, but also how well you collimate the beam, okay? So again, phase space volume and phase space density, important here. And talking about the X-rays, we'll talk about a phase space density as is appropriate in optics, okay? But let's appreciate what's going on here. We'll draw a typical picture of a phase space. Okay, so here are your 2 billion electrons. Okay. I drew the picture for 1 degree of freedom, but you can imagine a similar thing in a 3-dimensional physical space. This is a 6-dimensional phase space, right? We have the Q's, there'll be 3 for X, Y, and Z, and then the P's, right? PX, PY, and PZ. So that's a 6-dimensional phase space. Very hard to visualize that. Okay. And then I wrote the symbol T here for time evolution. Let's think about what happens if you have a bunch of particles. And what I did is I drew it like this. Let's take a second to talk about this. Okay. Now, here's almost a quiz question, which I could put on the exam. You know, sometimes people like to have short answers, multiple choice questions. I'm not going to do that for our class, but as you know, some instructors like to do that. So they might ask you about this picture. Is this a correct depiction? Okay. And here's the important thing. All right. Notice if it's true. Okay. We'll put this as a parenthetical remark, right? Because we're always searching for opportunities to review our foundation skills. So we know for some Hamiltonian systems, the momentum P is just a constant times the velocity, okay? So if P is some constant times Q dot, okay? What can we say here? Well, we would say here's a collection of particles. All these particles have a positive value for the momentum, okay? So you see what's happening. They all have a positive value for the momentum. If this is true, then all these particles would have, under time evolution, they would move to the right, and that's what we're seeing here. Now notice they're also growing, so P is actually increasing. So if P is some constant times Q dot, and we've seen that for a couple cases. For example, The simple harmonic oscillator. If you have a one-dimensional problem with a simple harmonic oscillator, then the momentum is just the mass times the velocity. This constant would be the positive mass, okay? But we've also seen this for the pendulum. For the pendulum, you could use an angle as your generalized coordinate, and then this constant is a little more complicated. You might see a mass times a distance squared, something like that. So if this is true, and if this is positive, okay, then for this picture, we have Q dot greater than 0. Okay, and that's what we're seeing here. You have a bunch of particles. You check back a little bit later, they've moved to the right along the Q axis. That completely agrees with what you have here, Q dot greater than 0. The other thing we're seeing is that P has gotten to be more positive. Okay, that certainly would not be true for the simple harmonic oscillator. You know, if we had a simple harmonic oscillator, these particles would be going around the origin. It wouldn't really be correct to say it's a circular orbit. And we mean it in the sense of a phase space orbit. But if this were a simple harmonic oscillator, then they would be going around the origin like so. And so this diagram is still correct. It just means we're looking at some other system, not a simple harmonic oscillator. So these particles certainly could move here. And a prime example would be some sort of unstable equilibrium. So Q dot is positive, Q is positive, and Q becomes more positive, P becomes more positive. This would be an example of something near an unstable equilibrium. We've talked about a lot of examples with unstable equilibria. Okay, so that kind of reality check is useful. Just to remind ourselves what's going on here with this is a phase space, right? This is a two-dimensional phase space drawn for a 1 degree of freedom problem. And sometimes we make very general remarks about Hamiltonians. Sometimes we make statements that are true about very special systems like kinetic plus potential. Okay, so for Liouville's theorem, we're going to consider a bunch of particles, and we're going to think about what happens under time evolution. So again, this little t here means we're thinking about time evolution. All right, so this theorem, we're going to approach this in stages, stage 1, stage 2, etc. Right. So the first thing we're going to do is think about a boundary. Okay, it's often said that these trajectories in phase space cannot cross. If you have two trajectories in phase space, if they reach the same point, then it's not possible for them to cross over. All right, we're going to make some remarks about that. Can we find pathological functions for which it's not true? And the answer is yes, you can find pathological functions for which two paths in phase space do cross. This appears to be a contradiction because it appears to contradict what we said about the existence of a vector field. Remember, Hamilton's equations give you a vector field on this phase space, right? At any point in this diagram, Hamilton's equations tell you there's a vector there telling you which direction a particle must move in phase space. Okay, so for example, this location, there's a vector. So that is the reason why you very often hear people say two trajectories in phase space cannot cross, they cannot intersect. The reason is, at the point of intersection, you would have a contradiction, right? Why would one particle go in one direction and another particle go in a different direction? Okay, we'll construct an example to show what's happening here. This is an example that will involve a little bit of funny calculus. But suffice it to say, for well-behaved functions, the statement is true that the trajectories cannot cross in phase space. And therefore, we can think about some particles. We can draw a boundary. Okay, and that's what I did in the diagram here. I drew a boundary around this collection of electrons. We got 2 billion electrons here. All right, and you can think about the ideal limit where you have an infinitesimally small particle neighboring another infinitesimally small particle, etc. You can build up a surface. So what I drew here is a solid line for the boundary. You can actually construct that in the limit by considering an extraordinarily large number of particles, kind of like a soap bubble. When you blow bubbles recreationally, you know, they float away on the wind. Think of something like that, a surface, which now moves through this picture, okay? We're interested in what happens to the volume of that surface. Okay, so we're going to investigate a surface, okay? The name of the surface is this capital script italic S. Okay. So this is the surface at time t, and that's supposed to be an arrow. Okay. Sometime later, the surface will have moved. Okay, looking at this picture, let's draw it like this. Okay. So using the dashed line, that was a stylistic element that allowed me to draw the surface at a different time while using the same color ink. So there's our surface, and this is at a later time. Okay, so that thing there is a lowercase Greek delta. You know, it's not the same as a partial derivative. A partial derivative has a loopy feature that goes the other way. This is a lowercase Greek delta, so one speaks of delta t. And we're gonna have to do that. We're gonna have different differentials. There will be an ordinary differential in a moment when we set up an integral. So in terms of the notation, let's just accept that we're using the lowercase delta, to indicate a small finite displacement along the time axis. There goes the surface. Let's investigate what happens to our surface. So now we're going to zoom in. Okay. And you know, for the current homework assignment, I did prepare a picture where I put a red rectangle and we zoom in on the red rectangle, right? That's in the homework 11 folder. Same idea. Let's zoom in. I used the red color. Let's zoom in. Zoom. We're going to zoom in on this region. Okay, and what do we see? It's like looking in a microscope. We're going to have a close look at what is going on here. Okay, so here we go. We're zooming in. So here's the picture that emerges as we zoom in on that region. There is, notice at this location in our picture, there's a portion of the surface. So let's draw that much bigger. Okay, so that was the surface. I'm using the same stylistic element. The solid curve, that's the surface S at time t, and here it is. Now you see we're zooming in, so later, okay. And again, the same stylistic element. Let's fix it up a bit here, like so. Yep. So this was at a later time. All right. Now the motion of the particles need not be perpendicular to the surface. Okay. In fact, in phase space, we don't have any notion of perpendicularity. Okay. We do have notions of area, but we don't have notions of angles in phase space because the different axes have different dimensions. All right, so let's focus our attention on a patch of air. If this is a surface, again, we're thinking of a higher dimensional surface, then it's logical to talk about some patch Okay, so there's a patch, and although in this picture it looks like a segment of a curve, a one-dimensional curve, we know that this is a higher dimensional discussion, and this higher dimensional discussion, okay, which is what we're doing here. We're going to call this a differential area, okay? So this is a differential area. Let's suppose the velocity vectors are like this, right? There is some sort of vector field here. So here go the velocity vectors like so, right? And this displacement vector, what's this displacement vector? It's the velocity vector times the elapsed time, which is our delta t, okay? So these are the crucial things now. We have this differential area, right? And again, it's a higher dimensional discussion, so we'll think of this as some sort of higher dimensional area, right? In fact, we know phase spaces are even dimensional, and so really this area should be some odd dimensional. It's certainly not square meters, okay? Because we'll have one other direction given by this displacement. Okay, so now we can say that the differential volume, okay, remember the notation, we use the lowercase delta, right? So we have a small excursion along the time axis here with a lowercase delta. The result is we have, and we do have the pencil available for shading. Okay, I'm trying to shade it. Oh, you know, I'm not so happy with my shading here. Trying to make it nice and uniform shading. All right, let's call that good enough. I don't want to get obsessive on the shading. So we do have this lowercase delta t, right? Delta t. That shaded volume, delta v. Okay, and so the notation is consistent because we're using this lowercase delta t for a small excursion along the time axis. All right, if you allow a time delta t to elapse, then the surface, this portion of the surface, sweeps out some volume in our higher dimensional space. And it's logical to use lowercase delta v. So this is a capital V. Sorry, we got to be very clear here. Capital V for volume, lowercase v for velocity. We're thinking of some general velocity vector field. Okay, that's a little unfortunate that we have two different V's in the discussion, but that's the way it is. Okay, so in summary, we can write down a formula for this. Sorry, this is one installment. Let me be careful. Okay, this is an installment. So this is a contribution to delta V. Okay, so the shading that we did there, that's a contribution to delta V. Let's write down a formula for delta V. The change, delta V is the change in volume. Okay, so delta V, we're asking the question, we have a volume enclosed by the dashed surface. We have a volume enclosed by the solid line surface. What's the change in volume? Well, we must integrate over the surface. So it has a very nice structure of a surface integral. So we're being very clear. It's a surface integral. We'll use a normal vector. Dotted into, that's lowercase v for velocity. Okay. dt, dA. Okay, and so let's just wrap up this discussion by observing, it does make sense to, we're following Taylor's notation here. We have the regular lowercase d. That regular lowercase d indicates we're doing an integral. So this is the differential for the integral. So this thing here, let's remark here, differential for the integral. Okay, so that's a remark on the notation. You see this integral here. So this is the integral we're talking about. We're doing a surface integral, and the differential for the surface integral is the dA. That's completely standard notation from calculus, right? We like to set up integrals. There's always some sort of differential. Everything else is a so-called integrand, right? So for this integral, the delta t is simply a constant. It's just some number, and we're going to form the quotient. Okay, so we'll divide both sides by delta t. The resulting object is a fairly standard difference quotient, and you see the structure that emerges here is we're going to form delta v over delta t. Oops, not my best delta. Thinking about too many things at the same time. Okay, we form this difference quotient, and you see, because we've been very careful to emphasize this delta t is simply a constant for this discussion, we can divide both sides by delta t, and now we have a surface integral, normal vector, outward pointing normal as usual, v vector, dA. Okay. Now, there are several things to be said here. We're going to take it up a notch. We have a very general theorem that if you have a surface integral, and if it's a closed surface, then this entire thing, by the divergence theorem, becomes an integral over the volume. So this is the capital V, the enclosed volume. As a name, we can use a cursive V for the name of that volume. The capital V was the value in cubic meters, but we also need a name for the set. So we'll use a cursive V. Those are logically distinct. This is an actual numerical value. This is a name. So therefore the capital cursive V. All right, and we're going to integrate the divergence. All right, dV. Okay, so notice this thing was the lowercase delta v. That corresponded to a lowercase delta t. We're thinking of some fixed amount of time, small fixed amount of time. Okay, here we're going to go to the limit. As delta t goes to 0, this becomes dv dt. Okay, so that's a separate installment of calculus. Limit delta t goes to 0. Okay, as delta t goes to 0, you see that delta v, the lowercase delta times the capital, not times, the lowercase delta capital V, also goes to 0. There's a sensible limit, right? That ratio approaches a limit, and the name of that limit is dv dt. Okay, so although this was a quotient, right? This was a so-called difference quotient, delta v divided by delta t. This is delta v, that's division, and that's delta t. This, as you know in calculus, this is a single symbol. This is the symbol for the derivative, and that's no longer division. This entire thing is just the symbol for the derivative. Okay, so this is the upshot of this discussion here. We've shown that the time rate of change of the volume, okay, and this capital V, without the there's no italics, this capital V, that's the volume measured in cubic meters. And we're talking about the time rate of change, the enclosed volume, right? That's a numerical quantity measured in cubic meters. The time rate of change of the enclosed volume, quite generally, it's an integral over the interior of the divergence of the vector field. Okay, so now here's the fun part. What we have done thus far is very general. We have not made any assumptions about Hamiltonian mechanics. Now we bring in Hamilton's equations. So now we have not done this yet. Now we will use Hamilton's equations, and I'll save time by just using a capital H for Hamilton. Hamilton's equations. Okay, let's talk about Hamilton's equations. Okay, it's customary in this business, right? In Hamiltonian mechanics, you very often use the following notation. Okay, you know we love to talk about a collection of generalized coordinates And it's very convenient to take those generalized coordinates and just encapsulate them into a single Q vector. And it's not necessarily a 3-component vector. It could have a very large number of components. But all of our generalized coordinates are here in this Q vector, the Q1 through Q lowercase n. All right. Now we've got, in the Hamiltonian worldview, we have Q's and P's, right? The same number of lowercase p. And these are coordinates on phase space. This collection, right, the Q's and the P's, that collection, 2n, right, there are 2n variables here. Right? And notice 2n is an even number. This collection of variables, we give it a name, z. Okay, so the z coordinates, these are coordinates on phase space. That's very important to observe here. Z coordinates okay. So this is important notation. It's very popular in Hamiltonian mechanics to use this notation so that we have a single variable z, collection of 2n, right? There are 2n variables here, and those are the coordinates on phase space. There are times we need to talk about the coordinates on phase space, and now is one of those times. So Hamilton's equations take the following form. Okay, Hamilton's equations, if you look at the chapter summary, hey, while we're on the subject, let's look at the chapter summary. I must alert you to a problem. And I understand many people these days use PDF files. If you have the PDF file, you too should look at the chapter 13 summary. Okay, here's the chapter 13 summary. I have a printed copy here. Can you see the problem? There's a problem right there. It says Pi is the partial derivative of the Lagrangian with respect to Qi. That's wrong. In the text, it's right. You have to differentiate with respect to Qi dot. Okay, so that's a typo. That's why I put an X. I don't often write in the book, but this is a typo. And the fix is simply to put a dot over that Qi. Okay, so I wouldn't want anyone to write this formula incorrectly on the final exam. That would be most unfortunate. Okay, just wanted to alert you about that, alert you to that. Hamilton's equations now in this Z notation look like this. Okay, Z dot, whatever that is, it's going to be Q dot vector, and here's the P dot. Okay, and now we use Hamilton's equations. And remember the agreement when we have these vectors, a single arrow denotes one free index. Okay, so this is equal to, we know from Hamilton's equations that the Q dot vector is the partial derivative all right, so far so good, right? This is one of Hamilton's equations that the Q dot is the partial of the Hamiltonian with respect to the P. If you ever forget the sign, just think about a simple non-relativistic kinetic energy. It's 1/2 mv squared, and you can very quickly get this, all right, the kinetic energy is P squared over 2m. So you can very quickly get this sign ironed out using that helpful trick. Right? Here we got the minus sign, and here you should think of the potential energy, right? If the Hamiltonian is kinetic plus potential, then this sign is precisely the familiar sign that the force is minus the gradient of the potential. Okay, so you see what's happening here. Again, this is our standard notation that if you have an arrow, it indicates a free index. You can get rid of all these arrows and just put a subscript I, perfectly equivalent. But it helps to understand why Here we're differentiating with respect to a vector. Again, the vector symbol just indicates a free index. So if you like, get rid of all these vectors and just put a subscript I. This will be Q sub I here. P dot I is minus the partial derivative of the Hamiltonian with respect to Qi. That's Hamilton's equations. Okay, now this is our vector field, right? Remember, this was the most fundamental realization about the Hamiltonian formulation of mechanics. We have the existence of a vector field. And to employ the discussion that we just went through here, this little v here, remember we're using lowercase v for a vector field. It's kind of like a velocity vector field. Okay, so there you have it. It is this vector field here. Notice this vector field has two n components, right? 2 times little n is the number of degrees of freedom. So this is our vector field, 2 n components. We need to know the divergence, and it's the divergence again using these z coordinates. Okay, so here we go. This is the fun part. The divergence. What is the divergence? The divergence of that vector field, okay, it is, we could write this for 1 degree of freedom or just go straight to an arbitrary number of degrees of freedom. We could write down a sum, I equals 1 to lowercase n, okay? And then we have the partial with respect to the Qi, partial h, partial pi, minus, there's the minus sign. Oops. Sorry about the writing there. And okay, sorry, I went off the paper there. So you see what happens, we have this vector field. We're gonna form the usual notion of the divergence. So we must start walking down this list of coordinates, right? We have coordinates on phase space here. We proceed through our list of coordinates. We must differentiate the vector field at that index with respect to that coordinate. So as we march along this list of coordinates, first we get a bunch of Q derivatives, and those are Q derivatives of the partial derivative of the Hamiltonian with respect to a P variable with the same index. So that was this collection of n terms. There are n terms here for the first part, right? Now we continue with the definition of the divergence. Now we must differentiate with respect to P variables, and we must differentiate the appropriate components in our vector field little v. And here's where we have this minus sign that's so important to us. So you can see this is 0 because of the equality of mixed partial derivatives. Okay, so there you have it. That's not a capital Q, it's supposed to be a 0. Can I make a better 0? That's pretty good, yeah. So it's 0 because of the equality of mixed partial derivatives. So that's very important to us. Okay, so having done that, we've shown that the volume in phase space is preserved. So that was our goal. dv dt equals 0. Under Hamiltonian evolution, if you have a volume in phase space and you let this evolve under time evolution, the volume may change, right? It might even get filamented. That happens in some cases. You remember in our last meeting, we talked about the filamentation. If the filamentation goes on for a really long time so that the structure of the filaments becomes comparable to the individual spacing between the particles, then you have a problem in reinterpreting your volume. But this theorem here is a statement about an ideal volume with a surface that's a smooth surface. And under time evolution, the volume, the value of the volume in, I shouldn't say cubic meters because now we're talking about phase space. So the value of the volume And really, this is where people start talking about Planck's constant when you start quantizing phase space. Yep. So we have the constancy of the volume. So that's the Liouville theorem. And again, very important for studying Hamiltonian systems. Okay. So here's the plan, for this week. We're going to talk about chaos to appreciate that there's a whole kind of a whole world of physics that was a real surprise when people started using computers to analyze complicated mechanical systems and started learning about chaotic behavior, right? The realization that for hundreds of years, people focused on solving simpler problems. It's kind of like, why are you looking for your keys under the streetlight? Well, because the light is better here. Even though you lost them somewhere else, you're looking under the streetlight. That's supposed to be kind of a joke. Yeah. So people, the reason for that remark is people studied these problems where you could write down a simple solution, and they began to amass a whole bunch of problems. Okay. And this was dangerous and misleading because it seemed that all these problems were non-chaotic, right? You could write down simple formulas in many cases for the evolution of the problem. And we're going to quantify what it means to be chaotic, right? We'll talk about some of the hallmarks of chaos, exponential growth of small changes to the initial conditions, the so-called butterfly effect. If you have the planet Earth with the entire ecosystem and you make a copy of the entire planet and the whole ecosystem, just one little butterfly has its wings in a different position. And you let time go on, check back a year or maybe 100 years later, the two planets will be totally different. That's called the butterfly effect, that a very small change in the initial conditions results in huge, right? We have this exponential growth of small changes, okay, small displacements. So we'll talk about how to quantify chaos, okay? And so because of this, you effectively cannot predict the long-term behavior of a chaotic system, right? In terms of actual laboratory experiments, you cannot measure the initial state with infinite precision. You would need to measure the initial state with infinite precision to predict the future behavior, because the tiniest difference in the initial conditions, you have this exponential growth. There will come a time where that exponential growth makes any small change in the initial conditions very noticeable. Okay. And another kind of general remark, this isn't a theorem, but a general remark is that often nonlinear systems exhibit chaos. And that's what we're going to see. We're going to investigate the damp-driven pendulum. So here's a motivational pitch for our discussion. In chapter 12, we're going to investigate the damp-driven pendulum. This stuff, chapter 12, is not on the final exam. However, the damp-driven oscillator is on the final exam. So our discussion of the damp-driven pendulum will be very useful, because anytime you can revisit a topic, in this case, chapter 5 and the damp-driven oscillator, anytime you can revisit a topic from kind of a different perspective, you profit immensely. So let's talk about the comparison here. We have in chapter 12, the damp-driven pendulum. They're both 1 degree of freedom problems. So let's compare the damp-driven pendulum. I'm going to actually scoot this like so. So let's do a comparison. So here's chapter 5. You know you need that stuff for the final exam. Chapter 13. Not on the final exam, but very useful to understand and compare. So we're going to study the DDP, the damp-driven pendulum. In chapter 5, we studied the DDO. Damp-driven oscillator. Okay. This one, this is the important, oh, thank you. Thank you so much. I really appreciate somebody caught, yeah. Uh, yeah, I feel bad. I better write this out. 12. 12, not on final. Thanks very much. This could have turned into an international incident. Okay. Yeah, do you appreciate that? And the chat window. Yep, very nice chat window. Okay, so let me try this again here. What I would like to emphasize here, we have formulas, closed form expressions. Okay, that's one way to say we have formulas. Standard functions. Right? Sines, cosine, etc. Okay. So for the DDO, we have formulas, right? And you're responsible for these formulas on the final. What do we have over here? Chaos. So that's a very dramatic comparison. No formulas here. Okay, that's the crucial thing. For the damp-driven pendulum, you cannot write down a nice simple formula for the long-term evolution. Okay, no formula. They're both 1 degree of freedom. Let's put that here. I think we can put this like so. 1 degree of freedom. 1 degree of freedom. Okay, let's just really emphasize that it's useful to compare these two problems. Okay, and so let's take a quick second to talk about this. For the damp-driven oscillator, we know the so-called asymptotic behavior. We had a formula. We studied the resonance. We spoke of capital Q, right? The quality of the oscillator. And we also know that there are these so-called initial conditions. So when you write down these formulas, there are enough free parameters so you can match the initial conditions. Okay, so those words are very important here. We do have formulas, and the formulas kind of naturally have a structure. There's a solution to the so-called homogeneous problem, and there's a solution to the so-called inhomogeneous problem with the driving force. The second D is the driving force. The driving force is responsible for the long-term behavior. And remember, the long-term behavior, the asymptotic behavior, in the language of chapter 12, it's called an attractor. Okay. Here we call it the asymptotic behavior. In chapter 12, we'll call it the attractor. This attractor had a very well-defined amplitude, and there was a phase shift relative to the driving force. Okay. So these are some of the amazing results from chapter 5. We could solve this problem. And now I know that is also covered in the first year physics course, but here we really want to have some clarity on how the structure of the solution allows you to match the initial conditions. There are free parameters available to match the initial conditions. Those free parameters are in a part of the formula that decays away. So the initial conditions decay away, they exponentially decay away because of the damping. The first D is the damping. And the long-term behavior, the so-called asymptotic behavior, is governed by the driving force. Okay, so we have those formulas in chapter 5. Here, we do not have the formulas, we have the chaos. So let's appreciate the system. All right, it's interesting to observe, this is a 1 degree of freedom problem. Okay, another chaotic system that we have alluded to over this summer session is the double pendulum. Compare, and I'll put this here as a remark. This will be a quick kind of parenthetical remark. Compare the double pendulum okay, this has 2 degrees of freedom. Okay, that is to say lowercase n is equal to 2. No damping, no driving force. Okay, so that's a quick remark, and that's the motivation. In chapter 12, Taylor would like to do a very detailed analysis of a chaotic system. We could have studied the the double pendulum. And recently, as part of this effort to bring programming to the upper division courses, we did prepare a nice, it was an effort that involved several people. I wrote some code, and then other contributors really served to make it a wonderful code with animations of a double pendulum and wonderful, amazing plots that you can share with people to show that this problem here, the double pendulum, no damping, no driving force, okay, 2 degrees of freedom. That's the problem. At 2 degrees of freedom, much harder to deal with, but with a computer, you can certainly do this. And not only the issues with the computer, but in terms of producing plots, right? If you have 2 degrees of freedom, phase space is 4-dimensional. Now that gets a little bit more difficult to visualize a 4-dimensional phase space. Here for these two problems, we have 1 degree of freedom, so the phase space is 2-dimensional. We can make some very nice pictures of what's going on in phase space. Okay, so in chapter 12, Taylor had a choice. Do we do a detailed study of the double pendulum, or do we do a detailed study of the damp-driven pendulum? He selected the damp-driven pendulum because it's a 1 degree of freedom problem. All right. Okay, so for the damp-driven pendulum, let's draw a picture. We have a pivot. Okay, so that's a point in the laboratory that's fixed. Okay, from time to time, we would draw a picture where there's like a concrete ceiling and we would suspend the pendulum from the concrete ceiling. That's not going to be acceptable here. We will often consider, in chapter 12, we will often consider the case where the pendulum goes over the top. Okay, the so-called rolling motion. Okay, so it's 1 degree of freedom. We'll introduce the usual phi angle. Okay, so there's our generalized coordinate, this angle phi. There are different ways to write the equation of motion. This is elementary. A fun way is to use the moment of inertia times the phi double dot. This equals gamma, the torque. Right? And we'll say some more words about this. You remember when we were talking about rigid body motion, the dancing T-handles, things like that. And we also had a homework problem with a spaceship, and we looked at the angular acceleration of the spaceship, okay? This formula that we've written here, this particular formula comes from first-year physics. If you have a fixed axis of rotation, which is appropriate language here, I'm gonna carefully hold the pen. I'm holding the pen perpendicular to the paper without endangering the document camera at all. I got a healthy 10 centimeters of space. This is the fixed axis of rotation, okay? And you will recall from your first year physics course, if you have a fixed axis of rotation, then we have a structure like this. It's very similar to good old mass times acceleration equals force. Okay, there was a little slowdown on the document camera, but we got through that. So this formula is precisely what you need for the equation of motion. Let's just skip, much of the setup here is elementary physics, so we'll get right to the, the differential equation. We got a phi double dot. We like to use this lowercase b when we talk about damping forces, so there's a b over m, phi dot. G over L, obviously L is the length of the pendulum. G is our familiar 9.8 meters per second squared. Here's the nonlinearity. This is kind of the P in pendulum, let's see if I can move the document. The P in, here's where we get some nonlinearity. We have damping, we have a driving force. Those are the forces, right, that are important to us here. Here's the nonlinear force. Here's the damping force. And then we have our driving force. There's some sort of amplitude, let's call it F naught. Okay, and remember, this omega here is determined by the laboratory apparatus. So when you're in a laboratory, you choose the frequency of the driving force. That is logically distinct from this, the G over L, right? You know, the square root of G over L would be the natural frequency for a pendulum with small oscillations. So we have those two different time scales. So having said that, we can rewrite this. You know, we like to introduce the beta. And experience tells us it's useful when you define the beta to incorporate a factor of 2 like it is shown here. Here's the omega naught squared I just mentioned. The crucial nonlinear term here. And here, it's useful to describe this amplitude. Remember, we originally used an F naught for the amplitude. It's useful to have this as a multiplicative factor, a gamma. So that's a pure number. You can see it's a pure number because we define it like this. Okay. So this gamma here, this becomes a knob that we can adjust, right? We're adjusting the magnitude, the strength of the driving force. Special case, if gamma is 0, then you have no driving force and you have just a damped pendulum, right? Here's the nonlinear term from the pendulum, right? Obviously we have some trigonometric stuff going on here. Here's our damping force, okay? So if gamma is 0, you recover the damped pendulum. And then for very small values of gamma, we can start to talk about the behavior of the solution. Okay, so the comparison in chapter 5, right, we didn't so much use phi. We would typically use an x, but you see the differential equation, I won't write it out, but over here, the left-hand side of this discussion was devoted to chapter 5. We had very familiar terms. We had an x double dot. We had this coefficient times x dot. That was our damping. And then the crucial thing, we had the omega naught squared times x, right? We had a Hooke's law restoring force. It's a plus sign if you bring it onto this side of the equation. It's a minus sign on the other side. So this term here, I might as well write it out. We had the x double dot plus the 2 beta x dot, right? That's lowercase beta, plus, and then we had the omega naught squared x, right? And then we had equals our driving force. But for the moment, we just want to focus on this structure. So the crucial thing now as we go into chapter 12, this nonlinearity, it's essential to have some nonlinearity if you want to see chaos. Okay. So we're going to start with some investigations, and here's where a computer becomes a wonderful tool. The one difficult issue is how can you reliably solve a differential equation on a computer? In some sort of ideal world, you would step along the time axis with infinitesimally small steps. Right? In actual practice, you need to choose some small finite step. Okay? And there are libraries full of books on how to solve differential equations on a computer. How can you make statements about the accuracy of your solution? The solution is worthless without some sort of statement about its accuracy. Okay, so solving differential equations on a computer is kind of a delicate affair. So this is an ODE. This happens to be an ordinary differential equation. Solve on a computer. Okay. So when you take, we have courses devoted to Python. We'll talk about, in those courses you talk about some of the subtleties here in the solution. Okay, so we've reached the 2 o'clock hour. I will stay here for questions. I'm just going to stop the recording.